What's up, you guys? Yes, welcome back to another PY212 review video. My name is Seven.
I'm Roger.
And I'm Mark.
And today we're going to be talking about EM waves. Let's go!
Let's go!
Let's go!
All right, guys, so let's talk about EM waves. So an EM wave is basically just a transverse wave of the electric and magnetic fields that propagates through space. So here we have a diagram of what that looks like. We can see that the electric field oscillates in the x direction, and the magnetic field oscillates perpendicular to that in the y direction, which is out of the board. And this entire wave is going to be propagating in the z direction. So we can actually encode that in these formulas right here. So these formulas might look kind of complicated, but we're going to break it down step by step. So the first thing is E0 and B0. These just give you your maximum magnitude of your electric and magnetic field. So that's going to be the value at the peaks, or it'll be the negative value at the troughs. But that just tells you basically how big or how strong the fields are going to be. And those values are actually not entirely unrelated. The E field is actually equal in magnitude to C times the B field, where C is our speed of light, 3 times 10 to the 8 meters per second. And then we have the sine function here. So this sine function basically tells us that it is a wave. And what we have in the sine function might look kind of complicated, but it's actually just tells us that it's a wave both in space and in time. So here we have kz, where z is our space coordinate. So if we imagine that t equals 0, so we're at like a frozen point in time, this just tells us that if we walk along the z direction, we're going to trace out a sine wave, which we can see here. As we go along z, it goes up and down like a sine wave. So that's pretty simple. And then omega t just tells us how fast we're moving through space. So if we stick with a certain point on the z-axis and we evolve the system over time, so we increase t, we're going to see that this peak is going to start moving to the right. And we're going to see entire waves start moving to the right as we start increasing the time variable. So that's all this means. It's just a wave in space and a wave in time because it's moving to the right. Another thing that you can do with this is you can tell the direction of the propagation. So if we look, the variable here, z, tells us that our wave is moving on the z-axis. And if we look at the sign, that tells us the direction. So the sign is actually the opposite of the direction. So we have a minus sign, which means we're moving in the plus z direction. If we had a z plus omega t, that would imply it was moving in the negative z direction. And same as if this was x or y, an x minus would be moving in the plus x direction, a y plus would be moving in the minus y direction, and so forth. And then finally, we have the vector directions. So this tells you the direction of oscillation of your waves. So we have E oscillating in the I-hat direction, or the x-axis, and B oscillating in the j-hat direction, or the y-axis, which we can see right here. And another important thing about that is that if you take the cross product of E and B directions, which I will write like this, so take the E direction cross the B direction, you will end up getting the propagation direction, which I will write here with p hat. So in this case, E cross B is going to equal the k direction, which makes sense because we have I cross j, which we know equals k. Great. And then there's one other thing you can do with this, which is calculate the Poynting vector. So the Poynting vector basically tells you how much energy, what's the rate of the energy that this wave is going to be delivering. So the Poynting vector, S, is going to be equal to 1 over mu naught E cross B. And the unit of that is going to be watts per meter squared. So basically what this tells you is over a given area, how much energy is this wave going to be delivering per second? And that is a very useful quantity to know for many different purposes. Okay, so one thing about EM waves is that they have this property called polarization. So if we imagine that we have an EM wave moving towards you, you see that the electric field points one direction, the magnetic field is perpendicular to that. However, The electric field and magnetic field can be pointing at different angles and still be traveling the same way, right? Because the cross product is still pointing in the same direction. So this angle here that the electric field is at is what we call its polarization. So polarization is something that we can interact with the use of something called a polarizing filter, which will usually be drawn like this. So the polarization filter has an important property, which is its transmission axis. So the way that these interact is that if you pass a polarized EM wave through the filter, you will get an EM wave that is polarized in the same direction as the filter, but you're going to have a step down in intensity. And that step down in intensity is going to be equal to the initial intensity of the EM wave times cosine of the angle squared, and that angle being the angle between the electric field and the transmission axis. The magnetic field, we don't really care about it when we're doing this because we know it's always perpendicular to the E field, so we really only care about the angle between the E field and the transmission axis. And so what this means is that we can sort of figure out the polarization of light by seeing how it interacts with polarization filters, or we can reduce the intensity of light based on its polarization as well with the use of these filters. Okay, so we know about polarized light, but most of the light we interact with is actually going to be unpolarized, which basically means that you're going to have electric fields pointing in pretty much every direction. We assume that it's uniformly around a circle. So when we pass that through a polarizing filter, we're going to get light that is polarized in the direction of the transmission axis of the filter, but it's going to be decreased in intensity by exactly 1/2. And the reason for that is because if we know that each direction is going to be scaled down by the cosine squared of its angle, if we actually graph that here, we can see we're going to get some sort of distribution that looks like this, where we just want to take the average of this, if this represents the entire unpolarized light, and we're going to get 1/2 of the total intensity.
Hey guys, let's look at a discussion problem. So we're going to look at problem 3 from your last discussion, discussion 12. And this problem has 5 questions in it, and they all kind of build on and reinforce each other a little bit. So we're going to start with 3.1 over here. So what we're given is an expression in space and time for the vector electric field, and we're asked to find the corresponding magnetic field expression. And so for this kind of problem, it helps to start with a picture. So what I have here is our 2 perpendicular electric and magnetic field waves. And we're going to start by labeling our axes in this picture to make sure that they match the expression we're given for electric field. So let's start over here with this x. This x tells us that as we change our x-coordinate in space, our electric field magnitude essentially changes. So in this picture, that means that this direction here is our x-axis, because as we move our x-coordinate, our electric field starts up going up here, then it's decreasing, then it changes direction. So that's how we trace out our wave in space. That's that x-coordinate. Okay, now we also know the vector direction of our electric field, and that's given by this unit vector at the end here, j hat. J hat tells us that we should have our electric field vector here pointing in the positive y direction. And so to make our picture agree with that, I'm going to label this as our y-axis. Okay, now this picture for the electric field agrees with our expression here. But there's also something else to check, and that is this plus sign here. This plus sign tells us that along the x-axis, our electromagnetic wave is moving in the negative x direction. It's kind of the opposite of whatever this sign tells us. So in this case, our wave is moving to the left. Okay, and we're going to need to keep that in mind in order to fully get our correct magnetic field expression. But let's start with some basic building blocks of our magnetic field expression. So our magnetic field is also going to be a wave with an amplitude. So we can start off by writing an amplitude, B naught, and it's also going to be a wave, and the wave is going to be in phase with the electric field. And that means that if this is a sign, then our magnetic field better have a sign as well. Okay, and everything inside the sign has to agree with the electric field. But kind of as I write out this expression here, I also want to take a note of what each of these things are doing here. So first, K. K says that our electric and magnetic fields have the same period in space. So whatever this wavelength for the electric field is, it's the same one for the magnetic field. So that's the same. Now, okay, next is our X. Our X says that our electric and magnetic fields move along the same axis, this x-axis here, which is kind of intuitive. Our two fields move together. Okay, next is the plus sign. So that's kind of a similar idea in that not only do the two fields have to move along the same axis, but also the same direction along that axis. So in this case, both fields are going to move to the left as time increases. Okay, omega. Omega tells us that if we take a point in space and we look at the fields at that point as time evolves. So we're sitting at a specific point, but we're watching what happens to the fields as time increases. That process should have the same period in time for both fields. So they both move up and down at the same rate. Finally, T is the same. That should kind of make sense. Okay, we're missing our unit vector here. And this one is kind of the trickiest one to get right because the unit vector we place here actually has to agree with this plus sign. And what I mean by that is that we know from this argument that our wave is going to move in the negative x direction. But there's another way we can tell what the direction of propagation is. And that comes from our E hat cross B hat. And so in this case, we know E hat, J hat, B hat we want to find, so I'll leave that blank. And we know that this answer here has to agree with the negative x direction that we established by looking at this argument. So I'll label that as minus I hat. So normally we would have something like J hat cross K hat equals I hat, but there's a minus sign, so we know that this has to be a minus K hat. And that's what we put here. Okay, and this expression is pretty much complete, but there's one extra step we can take, which is to come back to this amplitude. Knowing the amplitude of our electric field immediately determines the amplitude of our magnetic field. And specifically, the key here is the speed of light that links these two. And so the amplitude of magnetic field is actually the amplitude of electric field divided by the speed of light. So that's our complete expression for the magnetic field here. Okay, that's 3.1. Let's move on to 3.2, which is kind of a continuation here. So 3.2 is asking us to, given an electric field amplitude for an EM wave, to find the magnetic field amplitude. And that's exactly what we were just doing at the end of that last problem. And so to find this, we're just going to divide our electric field amplitude by the speed of light. And that's going to give us 3.3 times 10 to the minus 7, and units, we could either figure out volts over meters per second, or we could just say it's magnetic field. These are all SI units, so this has to be Tesla. That's our SI unit of magnetic field. So that's just a quick check of converting from electric to magnetic field amplitudes. Now, let's look at 3.3. So now we're introducing our idea of root mean square, which is very helpful for waves. And so specifically, we're told the root mean square value of our electric field amplitude. And what we want is the average intensity of our wave. And intensity, whenever you hear that, you should think of this Poynting vector, S. And the reason is because of the units of this S vector, which we should know are energy per area per time. So this quantity here, it's a vector. It tells us where energy is flowing in our electromagnetic wave. How much energy is flowing through an area in a given amount of time. And this is none other than intensity. You can also think of this as power per area. Now, if we look at this expression for S vector, the Poynting vector, it's the cross product of our electric and magnetic fields. Both of these oscillate in time, and so unsurprisingly, this S vector is also going to oscillate in time. But we're not interested in those oscillations. We're interested in the average here. So that's why at the beginning of this problem, the way I denoted what we're looking for is actually the average magnitude of our S vector. We don't care about the direction here of where our energy is flowing. We just care about the magnitude of this intensity and the average of that. And so to find that, we can rewrite what we're looking for, and we should recognize that this cross product is going to be easy to deal with, actually, because we think of our electromagnetic waves, E and B vector are always perpendicular, no matter what. Any point you take here, E and B are always perpendicular. And if we're thinking magnitudes, that means this cross product is just a multiplication. And so if we're thinking RMS, root mean square, the way we find the root mean square of our S vector is just by multiplying the root mean square of our electric and magnetic fields. Now, what we're given is this, the RMS value of our electric field. So let's convert our magnetic field RMS to the electric field RMS. And that conversion, again, is going to be what we've been doing here by using the speed of light. So if amplitudes are proportional like this, then RMS values are as well. So specifically, we're going to get something like this. This expression equals the RMS value of electric field squared divided by mu naught times the speed of light. And so now we can just plug in some numbers and get 100 squared, 4 pi times 10 to the minus 7 times 3 times 10 to the 8. And if we cancel these a little bit and see what we get, we should get 27 about. And the units, this is important, coming back to our discussion here, power per area. And that should tell us that the correct unit is watts per meter squared. And so this tells us the average intensity being carried in our wave here. So our wave, it carries energy, and so this is something we can measure. Okay, now let's look at 3.4, where now we have our electromagnetic wave like this, but now it's hitting a certain surface with an area, and over an interval of time, that surface is absorbing some energy. So first let's think about the picture here. So we have our electromagnetic wave, and now let's add some surface here. I'll draw a little square here, kind of, and I'll label that with some area A. And so what's happening is, so imagine, remember this wave was moving in towards the left, but let's imagine for a second that things are kind of flipped and our wave is moving to the right. And our wave, part of it is hitting this area. That wave is carrying energy. And so part of that energy being carried is being absorbed in this surface. And whenever we think energy, we should immediately think of our S vector, our pointing vector, because of the units, right? Our energy per area per time. So, the energy absorbed is going to be something like our energy per area times time times our area of our surface, A, times the time that we are exposing our surface to this wave, T. And this is almost right. You can see the units here make sense. Area will cancel with area, time with time. We'll be left with an energy. But again, here we're looking for a constant value. But this thing here, remember, it oscillates in time, right? So this value here is going to be changing in time. And so since we're waiting for 10 seconds, which is many, many oscillations, what we really care about is the average, right? Very often, or almost always, I should say, with light, we're measuring time averages, so over many cycles. And so this quantity here is exactly what we were looking at in the previous problem with this SRMS. So let's actually write that out. Okay, now we have our expression that we're looking for. And now, before we were given our root mean square electric field. And so now we're given our electric field amplitude. So we're going to find this root mean square intensity a little differently here. So specifically, we're going to write this out as, if we're looking at this expression here, our root mean square squared is the same thing as our amplitude square divided by 2. And we have our speed of light. So the same expression we were looking at here, but there's a factor of 2. And again, the reason that factor of 2 keeps appearing is an average of a sine squared function. So remember, if we square a sine wave, we get something that peaks at 1 and oscillates from 0 to 1, and so on average, it's about a half. Okay, now we can add in the rest of our expression here, and we can plug in some numbers. So we're going to get 100 squared here times 1 centimeter squared. We're going to have to take care of that conversion because we're looking for meters squared, times 10 seconds over our mu naught times 2 times the speed of light. And to save us some time here, we can combine all those things, and we should get something like 13 millijoules. And again, the unit, joules, is going back to how much energy. We're looking for an energy. The energy that's absorbed by our surface in 10 seconds. Right? So this is something we could measure. Okay. Finally, let's look at problem 3.5. So in this problem, what we have is essentially a light bulb with some power. In this case, it's 100 watts. And we have a surface some distance d away with some area a. And we're given both of those values. And what we're looking for is the force that this surface feels. So we've said that our electromagnetic wave carries energy, but it also carries momentum. And that's important because when we think of a force, the units of force, newtons, are the same as the units of momentum. So we could think about the momentum hitting our surface over a time interval. So delta P over delta T is the unit of force. And in this case, there is a detail that we have to keep track of, which is this reflection versus absorption scenario. So in this case, we're specifically told that our light is completely reflected. So I've tried to draw that here where we have essentially our wave coming in, and it's coming back out with the same amplitude, same everything. And so we have reflection here. And that's important because if we think of our force, then there's a difference between absorbing the momentum that's hitting your surface versus reflecting it back. And the difference is a factor of 2. So in this case, actually, the difference between the momentum coming in and coming out is 2 times whatever the momentum coming in is, because we're essentially having an equal and opposite momentum after reflection. Okay, now, we have to figure out what this momentum per time is. And the way we're going to do that is kind of indirectly by coming back to our energy per area per time. So the per area per time kind of idea should make sense here, right? We have an area, so we want some sort of per area idea to find our force here. But instead of energy, we want momentum per time. And for that, we're going to need to know for a given amount of energy in our electromagnetic wave, how much momentum is it carrying? And that conversion is actually, again, going to be the speed of light. So this speed of light, it's very much a fundamental constant, and that's one way to think of it. So the way we're going to do this is first, before we tackle this question, we're going to ask, of the energy coming out of this light bulb, how much is actually hitting our surface here? And the way we're going to do that is we're going to imagine a sphere around our light bulb, a tiny part of which is our surface. And so the reason that helps is because we have uniform isotropic illumination. That means in all directions we have the same amount of energy and momentum going out. And so what that means is what we want to find here is a ratio, essentially. We want to find of the area of our sphere here, the surface area, what part of it is the surface that we're interested in. And so that ratio is going to be our area divided by this surface area of our sphere, whose radius is this distance here. And so if we work that out, that'll be 1 centimeter squared over 4 pi times 2 meters squared. And that should equal something like 2 times 10 to the minus 6. Okay, and that's a unitless number. And so once we have that, let me kind of divide our work here a little bit. This is the ratio of the energy coming out of this light bulb, how much is going to this surface. And so one way to think of that is the power from this light bulb that we care about, which I'll denote as power surface, is a fraction of the light bulb power. And this fraction is 2 times 10 to the minus 6. And so in this case, we would get something like 2 times 10 to the minus 4 watts. And so that's telling us the energy per time that's hitting our surface. But we want momentum per time, right? Remember, our force is a momentum per time. And for light, energy per momentum is the speed of light. That conversion there from energy to momentum is the speed of light. And so the way we can use that, if we think of our watt as an energy per time, we get momentum per time for our surface is the same as this P surface, but we need to divide by C. And the reason we need to do that is to convert from energy to momentum. And this is almost, this momentum per time, it's almost the same as this force, except for this factor of 2. Because whatever momentum is coming in, it's also coming back out. And if we kind of combine that, I'll draw here. Our FA is 2 times P surface over C. Now we just combine everything we found. We get something like 2 times 10 to the minus 4 watts divided by 3 times 10 to the 8 meters per second. And that should equal approximately 1.3 times 10 to the minus 12 newtons. So that's our force right there. Right? So we have a light bulb, we have a surface, and that surface actually feels a force pushing it away from the light bulb, which is pretty crazy to think about, but the reason it doesn't feel like that's the case, maybe, is because of how small these forces are. So this is the same idea that you used in your homework for the solar sail. You literally have a sail, and the sunlight hitting it will push the solar sail. Okay, so that's all of problem 3. Hopefully you were able to follow some of these later problems here. But yeah, I hope that was good, and